In this video, I'm going to talk about SymPy. SymPy is a Python package, a Python library for symbolic mathematics. In this video, I'm going to show you how you can create symbols with SymPy and how you can make simple calculations using SymPy. So here I am in a Jupyter notebook. I'm using here VS Code, so I'm editing this Jupyter notebook with VS Code. And SymPy is a symbolic computer algebra system. What this means? This means that numbers and operations are represented symbolically, what allows to obtain exact results. So to understand what this means, what are the consequences of a symbolic computer algebra system, let's take a look in what it's not a symbolic computer algebra system. So here I have the math module. This math module comes with Python. You don't have to install it. This is already installed in your computer if you have Python. And I'm importing this math module and I'm using it to calculate the square root of 2. So let's execute this cell, and we have here the result. The result is 1.4142 and so on. Now, we know that if we square the square root of 2, we must have the number 2, right? So let's execute this cell and see we don't have exactly 2. We have here 2.00000 so on, and we have here this number 4. This happens because the way the computer deals with float numbers. I'm not going into details in floating point arithmetic in this video. I always have articles in my website chemistryprogramming.xyz, so you can see here more details about this floating point arithmetic. You have here some links to understand why this happens and what are the consequences. But what I need you to understand is that this is not exactly 2. And we know that it should be exactly 2, at least from a mathematical point of view. And if we try to make this equality, we have the result false, because 2.0000004 is not equals to 2. And this is something that sometimes beginners are not aware of and can lead to some problems in their calculations and their code. You have to be aware of floating point errors, and this is a case of floating point errors. Computers deal with float numbers in a way that sometimes can be misleading. Okay? And that's why in some contexts makes sense to use symbolic computer algebra systems. And this is where SymPy shines. You can install SymPy with pip install SymPy, and let's import SymPy with simply import SymPy. Now, let's do the square root of 2 using SymPy. See, we have here simply the square root of 2. You don't have here the result, the approximated result, 1.4142 like we saw here in the beginning. We have here the symbolic representation of the square root of 2. And if we square the square root of 2, you have the number 2. And this is what we expect from a mathematical point of view. Now we can make this comparison here. We can see that we have this result as true because this left side equals to the number 2 and 2 is equals to 2. So we have here a comparison that results in true. And that's what is expected from a mathematical point of view. And that's the power of a symbolic computer algebra system. Okay, so let's do again a square root, this time the square root of the number 8. We know from mathematics that this is a square root that can be simplified as 2 square 2. So let's take a look in the result. We have here 2 times the square root of 2. This is what is expected from a mathematical point of view because we can represent 8 as 2 times 2 times 2, and this is the same as writing 2 to the power of 3, and we can simplify this inside the square root as 2 times the square root of 2. So that's why the result is the way it is. And just for the sake of comparison, we have here the square root of 8 using the math package, and we have here just an approximation. Okay, this is the approximated value of this exact representation. Now let's go deeper into math with SymPy, basic mathematics with SymPy. First, let's remember that Python has an integer type, so here we have an integer, a float type, so here we have a float, and we also have a complex type that I'm not going to cover in this video because I'm going to make a video about complex numbers in the near future. Okay, so we have int and we have float, and I'm not going to cover complex numbers right now. And if we divide 1 by 1, even though these are integers, the result is a float. And if we divide 1 by 7, we have here a floating number result, and this is just an approximation again. Okay, so this is an approximated value of 1 divided by 7. Now, let's take a look at how SymPy deals with rational numbers. And SymPy have this simplify function to which you can pass a string representing a division. If I execute this cell, we have here a symbolic representation of the division of 1 by 7. And if you are lazy enough to not want to type all this simplify name, you can just type a capital S and we will have the same result. Okay? And the type of this result is the rational type. It's a class inside SymPy. So you can actually call this class passing the numbers, and you also have the same result. And what's more interesting is that SymPy can make some calculations using these rational results. As you can see here, if I run this cell, I will have the rational representation of this summation between 1 divided by 2 and 1 divided by 3. And you can make this summation in a piece of paper, and you're going to see that the result is this one, 5 divided by 6. And SymPy also deals amazingly well with this kind of situation where you have here a division using a rational type and int type of Python. So we have here the same result, 1 divided by 7, in the same way that we have seen here before. Since SymPy is a symbolic computer algebra system, it has some representations of common numbers, like the number pi. Let's run this cell, and we have here the symbol for the number pi, and its type is pi. But even though it's a symbolic package, you can ask for a float approximation using this method called evolf. So running this cell, you have here an approximation for the number pi. And the result is a float type, but is not the same float as the Python one. It's a special type of float from SymPy. And if you are lazy enough to not want to type all these letters, you can use n as an alias for evolf. So you have here the same result. And what is more interesting is that you can have an arbitrary number of decimal places. If you pass here the number 50 for this n method, you can have pi with 50 decimal places. That's why it's a float type different from the float type that comes with Python, because you can manage the number of decimal places in their number representation. Pi is not the only symbol available, you have other symbols, so you can always check the docs for other symbols available in the package. One that I want to show you is that you have a symbol for infinity. So the symbol is just two O's side by side, and if I run this cell, you can see that we have here the infinity symbol. And its behavior is as expected for an infinity symbol, because infinity is greater than 100. So this is not just a symbol, its behavior, it's what is expected from a mathematical point of view for an infinity. How can we create our own symbols? We know from Python that if we simply type here x plus 2, it will raise a naming error because x is not defined. But we can assign a number for the variable x, and now it will make sense because x being 2, if you sum 2 plus 2, it will result 4. That's what is expected from a Python point of view. But using SymPy, you can create the symbol x. And now, if we run this cell, you actually have the symbolic representation of the summation of x plus 2. And you can create as many symbols as you want. Here I am creating y and z and writing an expression with x, y, z, and the integer 5. So here we have x plus y plus z minus 5. SymPy has some symbols. We've already seen the symbol for pi, for the infinity, and SymPy has a symbol for I, for complex numbers, and it also has a symbol for e that we usually see when we are dealing with logarithms. Okay, and also has some other symbols that you can find in the docs. Now let's take a look at how SymPy deals with expressions, mathematical expressions. So here I am creating an expression. We have here 2 times x plus 3 times x minus the sine of x minus 3 times x plus 42. Okay, so I'm assigning all this expression to this variable here. So let's run this cell and let's see the result. See that we have here 2 times x minus the sine of x plus 42. So please note that SymPy did some math under the hood because we have here 3 times x and we have here minus 3 times x. So the result of these two is 0 and we only have here 2 times x minus sine of x plus 42. Okay, that's why we have here this result. So SymPy will do some math before showing you the result of an expression. But sometimes SymPy will not simplify the expressions for you. So for example, you can see here that we have this expression, okay? And from a mathematical point of view, you can probably see that you can simplify it. So you can pass this expression for the simplify function. And the simplify function will, as the name suggests, simplify this expression for you. Okay, so if SymPy doesn't simplify the expression for you automatically, you can ask using the simplify function. SymPy also deals with factoring and expansion. So I have here this expression that I'm passing for the factor function. And now I have the same expression but factored. Okay, and I can take this factor expression and expand it with the expand function. And now we have here this result that is the same of the initial expression. If you are dealing with trigonometric expressions like this one, so we have here the cosine of x plus y, you can expand it with this trig equals true as a parameter, and we'll have the trigonometric expansion for your expression. Finally, you can also substitute values in an expression. So I have here this expression, and it's simply sine of x plus cosine of y, okay? And I'm asking here using this subs method to substitute to replace x with 1 and y with 2. So I have here now cosine of 2 plus sine of 1. And I can ask for a floating point approximation using the AND method as we've seen before. So now I have here an approximate value for this expression. And finally, you can also make substitutions using symbols like the symbol of the number pi. And we have here the result 1 because the sine of pi is 0 and the cosine of 0 is 1. So 0 plus 1 results in 1. So this is it for this video. I have many more examples in this article at chemistryprogramming.xyz. The link will be in the description below. Here I have a full text explaining every step, and I also have many more examples that I did not cover in this video so that it will not be so long. If this video was useful for you, please give it a thumbs up and subscribe to the channel. I'll see you in the next video.